There we go. So does anybody have any questions before we get started? Any quick questions about anything? Okay, I don't see any questions, so we're going to go ahead. I do have a couple of announcements here. So we'll go ahead and get started. Yes, I will be going over the pre-lecture questions. Yes, there will be a tutorial next week. Okay, good. I don't see any other questions. So as you probably know, one of our topics for today is projectile motion, or as this guy's mom calls it, I think that's actually his teacher. Okay, by the looks of it, parabolic motion, and she's questioning his choice of display there for his projectile motion. Basically, you should never really be shooting things at your classmates. So going on to our announcements. So not only do tutorials begin next week, but office hours also begin next week. So I will be having office hours in BB Collaborate on Mondays and Wednesdays from 1 to 2 p.m. Okay. I'll probably have a few more office hours right before our midterms. I typically have a couple of office hours. So on the Wednesday office hours, we'll probably expand to say 1 to 3 p.m. or something like that right before our midterms. And then the TAs, so my office hours from BB Collaborate, the TAs office hours will be in Zoom. They haven't set their Zoom up yet. I have to send them another message and ask them to do that. But Hamidreza or Hammy's going to have office hours on Thursdays, and Guillermo is going to have office hour on Tuesday. And the tutorial schedule has also been posted in Canvas in the general course info module. So you can go have a look at who's teaching which tutorials. It's going to be Guillermo and Hamidreza, and then we have one more TA who will be teaching the third one. So I will answer questions about access codes at the end, but basically for the Achieve. But if you're going to take Physics 121 next semester or in the fall, you should purchase 2 terms. Otherwise, you only need 1 term. So any other questions, quick questions before we get started talking about physics? All right. So what are our topics for today? So as you know from the pre-lectures, right, our concepts for today are vectors, 2-dimensional and 3-dimensional kinematics, and a specific case of 2-dimensional kinematics, which is what we call projectile motion, which is essentially the motion of objects thrown near the surface of the Earth. Okay, so here are some of the comments from pre-lecture. One longer comment, but it was sort of a lot of people were asking very similar kind of questions. Where does the relationship between initial vertical velocity and vertical height come from? For example, when the vertical initial velocity of the 2 projectiles are the same, how do we know that the height of both will be the same or different? And then a lot of other comments about things like I'm a little bit rusty. Can we go over projectiles in 2D? Because physics was a long time ago. I know that's true for a lot of you guys. And then just we need more practice with the equations. So we are going to do a couple of examples today. Okay. So you can get some practice, okay? At least you can watch me do some of it, but for yourselves, the practice is going to come when you do it yourselves by doing the homework and in tutorial. Okay, so I did have some requests at the very end of class last time to go over this example. So I will go over this example first. So this is actually, even though it's an object going down a ramp, which is a 2-dimensional system, If we're just looking at the motion of the ball on the ramp surface, it's essentially a one-dimensional problem. Okay, and the question was, so the ball starts at rest at time equals 0. Suppose it moves 1 foot between time equals 0 and time equals 1 second. How far does it move between time equals 1 and time equals 2 seconds? Okay, so if you look at what they gave us, what did they give us? They gave us time information, and they gave us some position information, and they told us it was constant acceleration. So generally with a problem, the first thing you want to do then is say, okay, well, once you've sort of understood what they've given you, so what are the known quantities, is to think about which kinematic equation you might use. And in this case, because they've given you position information and time information, and they also gave you initial velocity of the object, they told you it starts at rest. So it seems like this kinematic equation might be a good choice, right? And if we think about it, so the other thing to be careful about here, and we'll see this in some of our problems, is that often you have to break up a problem into parts, okay? In this case, I've broken the problem up into 2 parts, and the first part is the motion for the first second when it's rolling, and the second part will be the motion for the second second. Okay, so for the first second, what do we know? We're going to say it starts at x0 equals 0. Its final position would be 1 foot, because it moved 1 foot in the first second. Okay, its final time is 1 second, and its initial velocity would be 0. And that's enough information to allow us to solve for the acceleration of the ball, right? We plug in all of those values there into our kinematic equation, and we get that the acceleration of the ball, this constant acceleration, is our 2 feet per second squared. Okay, so now this is in feet instead of meters, but that's okay. We can just do the whole problem using feet as our unit of length. Typically, we'll use meters and seconds. We'll use our SI units. And then, so now we have our acceleration. So now we can go on to the second part, okay? Or in fact, what we can do is take the same kinematic equation and solve for what would the position of the ball be after 2 seconds, okay? So how far away from where it started would it be after 2 seconds by taking the acceleration we've solved for, plugging it into our kinematic equation and plugging in time equals 2 seconds. And when we do that, we get that the final position after 2 seconds is 4 feet. So after 1 second, it's at 1 foot, and after 2 seconds, it's at 4 feet. But we're not quite done, because what they don't want the final position. What they want is how far it moves between 1 second and 2 seconds. And so in the second part, we need basically the displacement for the second part of the motion, right, which is the difference between 4 foot and 1 foot. So in the second part of the motion, it moved 3 feet. So that's why the answer to that one was 3 feet. Okay, and so it kind of makes sense, right? If something's accelerating, right, its velocity is increasing, then every second it's going to move more and more distance when you have a positive acceleration like this. So in the first second, it only moved 1 foot. In the second second, it moved 3 feet. In the third second, it's going to move 5 feet, and so forth. So any questions on that? I noticed that some people solved it a variety of ways in Achieve from your comments, and that was great. This is not the only way. Okay, this is sort of a very methodical way, and I'll do a lot of the problems this way, but there are other ways to figure this out. All right, so let's move on to our first topic for today, which is vectors. And this is a very quick review. They talked about vectors in the pre-lecture, and I'm assuming that you've run into vectors before, so I'm not going to spend a lot of time on vectors. So starting with our two-dimensional vectors, you can generally think of a vector as an arrow that has a length and a direction. Okay, and for a two-dimensional vector, there's typically 2 ways that you can specify or describe your vector. One way is to specify it with its magnitude, which is the length of the vector, in this case A, and its direction. In this case, we're using an angle theta measured from a horizontal axis to describe the direction. And that's very typical to use theta from the horizontal axis as a vector direction. But another way to describe the same vector would be instead to say what is the projection of the vector along the x-axis, the horizontal axis, called the x component, which you get from just basically calculate using your trigonometry, in this case a times the cosine of theta. And then what is the projection of the vector along the y-axis, otherwise known as the y component, ay, which is just the magnitude a times the sine of theta. So hopefully this is not new to you guys, that you've seen this before. And one of the most fundamental things with vectors is to remember that the vector is the same. This is the vector A in both cases, no matter how you choose to describe it. Okay, it's the same vector. So that's our two-dimensional vector. Okay, so what I thought we would do is I'm also hoping that you are already familiar with how to add and subtract vectors. They did talk about it in the pre-lecture. So we're just going to do a poll question here on vector subtraction. So have a look at this while I make up the poll. Okay, so we've got 5 choices here. All right, so vectors A and B are shown to the right. And the question is, which of those green vectors best describes A minus B? And if you can't see the answers, you can click that little X in the upper right, and it'll make the poll shrink for a little while. And then you can click down below where it says View Poll, and it'll come back again. All right, I think we're going to do 5 more seconds here. So if you're not sure, go ahead and guess. So 5, 4, 3, 2, 1. And let's see what everybody thinks the answer is. All right, so what do we see? We see that the majority, the largest group, are going for B, but there's a reasonable number of guesses for C and for D. All right, so let's have a look at how you would figure this out. So if you remember from when you've done vector and addition and subtraction before, if you want to figure out A minus B, essentially that's the same as A plus minus B, where minus B is a vector that points in the opposite direction as B but has the same magnitude. And that would look something like this. This is what A plus minus B. So remember, to do vector addition, you take the second vector and you take the tail of the second vector and you put it on the tip of the first vector. And then to get the sum, you draw a vector from the start of the first vector to the end of the second vector. So in this case, from the start of A to the end of minus B, and that would be answer B. So well done, everybody. Most people got that one correct, or a lot of people got that one correct, so well done. Okay, so this is your basics of vector subtraction. If you don't remember how to do this, I would recommend going back and reviewing how to do this in your previous physics books, or have a look in the e-text in Achieve. They have a nice section in the first chapter about vectors. Okay, so any questions on that before we go on? It's pretty important that if you don't remember how to add and subtract vectors, that you review it, because we will be using it quite a bit. For example, you might have noticed that one of the pre-lecture questions, so there are sometimes questions within the pre-lecture assignment, was about vector subtraction, because what they were asking you was to figure out the average acceleration when you were given two velocity vectors that look like this, v1 and v2. So v1 is our initial velocity and v2 is the final velocity. And if you want to figure out the average acceleration, you have to do a vector subtraction. You have to subtract v1 from v2. So again, just like we saw, if you want to figure out the vector difference here, okay, then you draw vector 2, v2. You add minus v1, that's our vector subtraction, okay? And then your average acceleration, right, which is the result of that vector subtraction, then you start at the beginning of vector 2 and you draw a vector that ends at the tip of vector minus v1. And that would be the direction of your average acceleration. Okay, to get the magnitude, then you'd have to take the size of that that difference, right, and divide by the time change, the t2 minus t1. Why do you have to subtract? Because it's v2 minus v1. It's the change in velocity. Okay, so whenever you do change in, it's always final minus initial. Okay, to figure out how much something has changed. Any other questions on that? And then t2 minus t1 is just a scalar, so that will change the numerical magnitude of the number and the units in this case. Okay, great. So most of the time, okay, you won't be drawing tip-to-tail vector drawings, because that's, you know, kind of time consuming. You have to get out a ruler, you have to figure out how long to draw your arrows and everything. It's much easier to add vectors using components. So for example, in this case, where vector C is the sum of vector A and vector B, if you want to figure out what vector C is, you just figure out what the x component is, and you get the x component of vector C by adding the x component of A to the x component of B. And you figure out the y component of C by adding together the two y components. Okay, so adding components, as we're going to see when we do velocities and accelerations, which are vectors, and especially when we do forces, force is also a vector quantity, that the easiest way to add things up is to find the components and add the components together. Yes, to get the magnitude, you'd have to divide by the change in t. Yes, that's correct, Prescott. So. Okay, so there was one thing they also introduced in the pre-lectures, which you may not have run into before, and that's this concept of what we call unit vectors. So unit vectors are vectors that have a magnitude of 1 and have no units. And we define them to point along specific axes. So in Cartesian coordinates, we have the unit vectors I hat and j hat. And I hat points along the x-axis and j hat points along the y-axis. Okay, and we always write them, whenever a vector is a unit vector, okay, we always write it with a hat over the top as opposed to an arrow. Okay, if it's a standard vector, I will always write it with an arrow, but if it's a unit vector, I'll write it with a hat. And they are a convention, a very useful convention to help us write vectors, and as we're going to see, manipulate vectors. Okay, so for example, if we go back to that first two-dimensional vector I introduced, vector A, if you wanted to write vector A using unit vector notation, you would write it as A is equal to AX I hat plus AY j hat. That's how you would write. No, you should always use a hat on a unit vector, okay? Because the hats designate that this is a vector that's only of length 1 and has no units itself. Okay, so that's actually pretty important that you always use the hat there. Okay. Well, the X and Y, just they specify which axis that component is. Okay, but they don't. We like to, if you want to represent it as an actual vector, like you can't say a vector is equal to ax plus ay. That would not be true, because ax and ay are scalars. Okay, so you have to add in. So basically, you can think of ax times I hat as vector pointing along the x-axis that has length ax, and you can think of ay j hat as a vector pointing along the y-axis that has a magnitude ay. So you can think of A as, in this representation, you're writing it as the sum of two vectors. Okay, a vector along the x-axis and a vector along the y-axis. And so this is what it looks like in 3 dimensions. Okay, we won't do a lot with 3 dimensions, but occasionally we'll do 3-dimensional vectors. You will do more 3-dimensional vectors in Physics 121, just to be warned for everybody who's going to do Physics 121. Okay, so a vector in 3 dimensions, you need 3 things to specify it. So you can either have your 3 Cartesian coordinates, ax, ay, and az, where z is our third axis, right? And remember, these the Cartesian coordinates, the Cartesian axes are all perpendicular to each other. Or you can use what are called spherical coordinates, okay, where you specify in terms of the magnitude a and 2 angles. In this case, our 2 angles are theta and phi. Okay, but again, don't worry about that too much because we won't be doing a lot of 3D, at least not this semester. Okay, and then, but then if you want to write this down, either you'd have to write down a and 2 angles, like magnitude and 2 angles, or you could write it in terms of 3 unit vectors. So now we've added a 3rd unit vector, which we call k hat, which points along the z direction. And then you can specify this vector, vector a, as being ax I hat plus ay j hat plus az k hat. So again, we're essentially saying that the vector A is the sum of 3 individual vectors, one along the x-axis, one along the y-axis, and one along the z-axis. Okay, and you can draw that out for yourself, those 3 vectors, and see that they add up to our vector A. So you might think, well, why bother? Why not just write down ax, ay, az? And the reason is that this unit vector notation will be especially useful later on when we start to do vector multiplication. We are going to start multiplying vectors. You're going to see there's different ways to multiply vectors. You can do what's called a scalar dot product, or you can do a vector cross product. Some of you may have run into these already. Okay, and unit vector notation makes those particular calculations a lot easier. So that's why we're introducing them now, so you get used to it. I don't understand your question, Samuel. Where does A in the spherical component? That's the magnitude of the vector. Just like in 2 dimensions, we had A and theta. Okay. Okay, so as we move from 1 dimension to 2 dimensions or 3 dimensions, okay, we can develop kinematic equations, right, for each dimension. And this is what they would look like. So this is our kinematic equations for our constant acceleration cases. Okay, so this is completely general now, okay, and essentially the main thing to notice here is that the motion in each direction is going to be independent of the other directions while the object is moving. So while a ball is flying through the air or a bird is flying, whatever the object is that's moving, okay, as long as it's moving unimpeded, okay, then the x component of the position and the velocity is only influenced by the acceleration in the x direction. What's going on in the y direction is only influenced by the y acceleration, and what's going on in the z direction is only influenced by the z acceleration. There are 3 completely independent basically motions, okay, that happen to be happening for a single object. So it is true that if something happens in the x direction that stops the object from moving, then it will also stop in the y. So if you throw an object and it hits a wall, yes, that will also stop it in the y. Or if you throw an object up and it hits the ground, okay, it goes up and comes back down and hits the ground and stops moving in the y direction, it will also stop in the x. Okay, so this notion of independence of motion it only really applies while the object is in motion. Okay, and you have your independent x, y, and z going on, but remember the time would be the same in all three sets of equations. The time is the quantity that sort of links them together. Okay, so now we are going to spend the rest of our time today, and as you probably know, this is one of physicists' favorite things, special cases to look at is what we call projectile motion. Okay, so projectile motion is a special case of three-dimensional kinematics or two-dimensional kinematics. And typically what we do is we label the horizontal motion, that we call that the x direction. Okay, so sort of parallel to the surface of the Earth. Okay, we treat the surface of the Earth as flat, right? Even though we know we live on a sphere, but if you look at a small part of it, it's flat enough to call it flat. So, and then the y direction will be our vertical direction. Okay, so vertically upwards or downwards from the surface of the Earth. We typically say positive y is upwards, away from the center of the Earth. Okay. And so if you look at, for our special case here, and we typically are going to ignore the z, you can arrange your x and y axes so that there's no motion. For projectile motion, there's no motion in the z direction. Okay, you just line up your x and y along the path of the object. Okay, and assume that it doesn't deviate in the y direction. There is no acceleration in the y direction, so there's no reason it should deviate in that direction. There's no velocity in the z direction, no acceleration in the z direction, so we ignore that. Okay, but if we look at what's going on in the horizontal and the vertical, we see that that we have for projectile motion, no acceleration in the x direction, right? Because gravity only acts in the y direction. So that means that our x acceleration is a constant equal to 0. And since the acceleration is equal to 0, that means that the x component of velocity can't change. So that means that your final x velocity will always be equal to your initial x velocity for projectile motion. Okay, so it's a constant. The horizontal velocity is a constant of the motion. And then the other thing that's a constant of the motion is the y acceleration. And the y component of the acceleration will always be equal to minus g. Okay, we always write it as minus g, and then we define g to be a positive quantity. So g, again, is equal to our 9.81 meters per second squared, the acceleration due to gravity near the surface of the Earth. And then because that's a constant and not 0, your y velocity will change with time, and your y position, of course, will change with time. And then if Vx is not 0, then your x position will also change with time. So these are going to be our projectile motion kinematic equations that we'll use to solve various projectile motion problems. Okay, so just to write what it looks like in unit vector notation, so you can see what it would look like. So again, so if we define x to be horizontal and y to be vertical, then for our acceleration, ax is 0, ay is minus g, where our g is our 9.81 meters per second squared. And so you would write your acceleration vector for a projectile as being minus g j hat, okay, which is a constant. So a constant in the negative y direction. And then you could write your velocity vector as we know that, again, that the x component is constant equal to v0x, and the y component will change, and it will change according to our acceleration, right? Our minus g acceleration in the y direction. And you would write your velocity vector, which will change with time, at least the y component changes with time, right? Okay, as vx I hat plus vy j hat. So that's how you would specify those quantities in unit vector notation. Okay, so just to have a little look at projectile motion, okay, and what the trajectory of a typical projectile might look like. So in this case, we have a projectile, okay, that's being launched with a velocity, an initial velocity such that the initial y component of the velocity is 19.6 meters per second, and the initial x component is 9.8 meters per second. And for this little diagram, they're just using 9.8 meters per second squared for the acceleration. Minus 9. Right? AY is minus 9.8 meters per second. So you can see what happens as our projectile moves. Okay, so it starts off with a vertical velocity of 19.6. Then after 1 second, okay, it had lost 9.8 meters per second of acceleration, right? That's what that negative acceleration, the acceleration in the negative y direction is doing for you. It's telling you that the y component of the velocity changes by minus 9.8 meters per second every second. So after 1 second, it went from 19.6 to 9.8. And then after 2 seconds, it drops another 9.8 meters per second. And so at the top of the arc, at time equals 2 seconds, the y component of the velocity has dropped to 0. And so you can see at the top of the arc, you only have a horizontal velocity equal to 9.8. So it's only got the x component. And then if you go 1 more second, okay, now this is where we turn around, right? Now that acceleration in the negative y direction is causing it to speed up as it comes down. Remember, we talked about this last time, how it's going to slow down as it rises and then speed up as it falls. So 1 second later, and we're now at minus 9.8 meters per second. And then 1 more second, and we're back to the ground again, okay? And now our velocity is minus 19.6 meters per second. Okay, this is all without any air resistance or other forces acting. Okay, so there's a lot of interesting things to notice here. One thing to notice is that it took 2 seconds to rise and 2 seconds to fall back to the same height again, to fall back to the ground in this case. So that's what I call the symmetry of the motion, that it takes the exact same amount of time to rise as it will to fall. Okay, if you do a complete arc, a complete parabola. Okay, and another symmetry to notice is that when the particle returns to its initial height, okay, its y velocity has the same magnitude, so the y component has the same size as it had when it launched, but pointing downwards instead of upwards. So however much upwards velocity it had to start, it will have that much downwards velocity when it gets back to the ground again, say if it started at the ground. So remember, this is only true when you get back to the same height again. Okay, so this is for the special case of where you launch and land at the same height, which will only be true for some problems, but a lot of problems that will not be the case. And then you're going to have to use your kinematic equations to figure out where it's along the parabolic path you are. So you can figure out what is the velocity, what is the position at that time. So just to talk really quickly through some of the checkpoint questions, because I know people wanted me to explain it, and then we'll do an example. Okay, so one of the first ones, most people got this one right. So this says a physics demo launches 1 marble horizontally, while at the same instant dropping a second marble straight down. Which one hits the ground first? And most of you realize that they hit at the same time. So you can see why that is if you look at our kinematic equations, okay? So for example, if we look at the kinematic equation for y position here, okay, we know that both marbles in this case have the same initial y velocity, right? They both start with 0 y velocity, okay? And they both fall from the same height. Okay, which means that they both also have the same initial y position and they have the same final y position. Y and y0 are the same. And if you go look at that equation and you realize that v0y is the same and y and y0 are the same, and they both undergo the same acceleration, then that tells you then that t has to be the same. So they must spend, if they both fall the same distance under the same acceleration, starting at the same initial velocity, it must take the same time for both of them. Okay, and it doesn't matter what was happening in the x direction, as long as the object didn't stop moving, as long as it was nothing in the x direction stopped it from moving, okay, then the y motion of both of these objects is the same, and they will both hit at the same time. Okay, and it's really important to keep that independence of the x and the y in mind with these problems. So that also applies, okay, for this problem. So we had these two 3 ships problems. Okay, the first one, called 3 ships version 1, said that you have a destroyer and it simultaneously fires 2 shells with the same initial speed at 2 different enemy ships. The shells follow the trajectory shown which ship gets hit first. Okay, and the important thing here is to realize that the initial speed is the same, but the initial y component of the velocity is not the same here because they're fired at different angles. Okay, so you can see if you were to work out the components here, the angle theta is different in each case. And the one that's fired more straight upwards will have a larger initial y velocity. Okay, and so if you think about the y motion here and what that looks like, okay, basically, and keep in mind that your motion in the horizontal and vertical directions, those motions are independent, okay, and you look at only the vertical motion here, okay, do you think it takes longer for the shell to reach point A and fall back to the sea? Or do you think it takes longer to reach point B and fall back to the sea? So which of those 2 trips takes a longer time? You can let me know in the chat. Yes, exactly. A is going to take a longer time, right? It's a longer distance. Okay, why is it a longer distance? Well, because that projectile was fired with a larger initial vertical velocity. Okay, so it's going to take a longer time for its velocity to reach 0, and it doesn't turn around until the velocity reaches 0. Okay, so that entire trip is going to take a longer time because that projectile rises to a greater height and comes back down. Okay, so which gets hit first? Why, enemy 2 does, because the trip up to point B and back down is much shorter because the initial velocity, right, in the y direction there is smaller. It doesn't take as much time for the object to basically reach velocity, vertical velocity of 0 and come back down. Okay, essentially, the shell launched towards enemy 2 has a smaller initial y velocity and therefore rises to a lower height, and so we'll have a smaller air time. Okay, so how high you rise, okay, that's going to tell you how long a projectile will be in the air. Okay, provided there, like I said, there's nothing in the x direction to stop it moving, then it's the y direction that's going to define what happens here. Okay, and then again, same idea here. Okay, now the 2 projectiles are fired with different initial speeds, okay, but they go to the same height. And if they go to the same height, that means they're going to be in the air for the same amount of time. Basically, if they go to the same height, they have the same initial y velocity. Okay, and same initial y velocity, they will rise to the same height, and so they will be in the air for the same amount of time. And so both of these enemies will be hit at the same time. Hopefully that clarified that somewhat for people who were confused. But it's all back to that y kinematic equation telling us that you can figure out the time, basically, given the initial y velocity. So what I thought we would do for the rest of class is we're going to do an example problem. And so I'm going to switch slideshows. I have a second slideshow here. Okay. I'm going to end that one. I'm going to switch to this one. So yeah, it doesn't matter what X is at all. Okay, this doesn't seem to be switching for you guys, so I have to figure out why it's not switching for you guys. I think I have to stop it and start it again. Sometimes this doesn't behave the way I expect it to behave. Okay, so here's an example problem. As some of you may be familiar with, this is football, and here we have a field goal kicker, and the goal of the field goal kicker, as you probably know, is to try and kick a ball so that it goes between those two uprights there. Okay, but it has to go above the crossbar too. Okay, so we have a field goal kicker, and the field goal kicker is kicking the ball at 30 meters per second at an angle of 25 degrees above the ground. So if the crossbar, okay, which is we need the ball to go above the crossbar. So if the crossbar of the goalpost is 3 meters off the ground, how far away can she kick the goal? Okay, so if you think about what's going on here, right, you can see from that trajectory, if she's too far away, right, then the ball will be too low when it gets to the crossbars. So even if she fires straight at it and gets the sideways direction correct, it won't be high enough to cross the crossbar. And if she gets closer, okay, then it will be higher. So there's going to be some maximum distance, okay, that she can back up that corresponds to when the ball just clears that crossbar. Okay, if she were any further away, it would not make it. Okay, and if she's closer, then it definitely will. And so we're going to try and figure out what's the maximum distance that she can stand back and it will still clear the crossbar. Okay, so and that's going to be the distance when the ball just reaches that crossbar height. So for a projectile motion problem, the first thing I always do before I do anything else, okay, so there's our ball. Sorry, I forgot. We have, just to show you again, I forgot that our ball actually goes across. So this is what we're looking for, the ball clearing the crossbar. Okay, so the first thing I always do is I start writing down what I know, okay, and I go and figure out what my x and y components of my initial velocity are, because our kinematic equations, remember, are split up into x and y, and so we do need to know independently what is v0x and what is v0y. So here I drew in the angle 25 degrees. There's our initial velocity vector. I'm going to choose to have x0, initial position v0, and initial y position v0. If they're not given, you can choose that. Okay, it's your choice where you want to set x0 and y0 to be. So we're going to set our clock. So we're starting at time equals 0 when the ball is kicked. Okay, and then so what's our initial x component of the velocity? It's just 30, or 30 meters per second times the cosine of 25. And so that gives us our 27.2 meters per second. And our initial y component is then 30 times the sine of the angle. Okay, and these are both positive quantities. It's moving it, the ball's moving in the positive x direction and it's going upwards. So it has a positive y component of 12.7 meters per second. Okay, and we're trying to figure out that maximum distance. Okay, so that's our starting information at the starting point. Now if we go over to the right-hand side and look at where our field goal posts are, okay, and we say, okay, what would our final y be? So what should we set? Anyone want to give me a guess as to what should I set as our final y? Okay, so I have lots of suggestions that I should set it as 3 meters, and that's the right idea. The final position is when the ball is just clearing the crossbars. So my final y position is going to be 3 meters. So I have an initial y position of 0 and the final y position of 3 meters. Okay, now there's a bunch of things I don't know. So now I'm writing down my unknowns. I wrote down all my knowns. Okay, what are my unknowns? I don't know what x is. I don't know what the final x position is. I don't know how long the ball takes to get there. I don't know how fast the ball is moving in the y direction when it gets there. I know how fast it's moving in the x direction, right? Because it's the same as the initial. x component of the velocity. All right, so now what do I do? Well, now I have to figure out which kinematic equations to use. I'm trying to solve for x, right? X is my goal, okay? The maximum distance, right? When the ball just clears the crossbar. So I'm after x, okay? So I'm going to get your help with this. So I would like to know which kinematic equations should we use, or could we use to find x? What do you guys think? You can give me some guesses in the chat. Which ones do you think I should use? All right, so I have a vote for B. So if I B, what will I get out of B? Can I get X out of B? I can't get X out of B, right? But I can get time, right? Okay. So if I were to use B, okay, I could get time, and then I could use C. Right, exactly. Then I could use C to get X. Okay, so in this case, you're going to need two equations. Okay, so and that's often the case, and it's often the case that you solve in one direction for time and then use that time to figure out something in the other direction. Okay, that's a really common thing to do in projectile motion problems. So let's start with our equation B, our position, our vertical position equation. Okay, and we do in fact have all of those quantities except time, and so we can solve for time. So now this is one of these situations where, because this is a parabolic equation, we end up with a quadratic that we have to solve. And I'm assuming you guys know how to solve quadratics. Most calculators nowadays and computers can solve them for you automatically. And as we know, with quadratics, you get two answers. So there are two different times when the ball is at height 3 meters. And you have to say, does that make sense that there are two different times? But then you look at your trajectory and you say, yeah, that makes sense. There are two different times when the ball would be at 3 meters. One time on the way up, one time on the way down. Okay, and so the one we need of those two times is the time on the way down, right? So we have to choose the right one. The ball reaches this way twice, okay, and we're going to choose the second one, okay, because that's the one down, and that's will give us the maximum distance. And then we take that time, we plug it into our x position kinematic equation with the initial x velocity, and we get that our x, okay? The maximum distance back, okay, so she's actually a pretty amazing field goal hit. This is not super realistic, okay, because you can basically back up 63.4 meters and the ball will still clear the crossbar. Okay, so that's one way to do this problem. Does anyone have questions on how I did that? Okay, so just real quick, because we only have 1 minute left, you can do it with these three equations as well. So the other way to do it this way avoids using a quadratic. So if you don't like quadratics, there's almost always another way to do it without a quadratic, but in this case, it would require you to do three equations. Okay, and it looks something like this. First, you solve for the final y velocity, because you know the initial y velocity, you know the y displacement, you know the acceleration. You can get the final y velocity. Now you get a plus or minus there, okay, but we know that it's moving downwards, so the minus would be the answer. Okay, the ball again reaches the same y twice, right, and is going to have this basically, so that's why you get two values. Okay, but you choose the negative one, and if you choose the negative one, you can use that then to solve for the time, and you get the same time we got with the other method, that it reaches minus 10.12 meters per second at a time of 2.33 seconds. Okay, and then you go back and do what we did before, which is plug it into the x equation, and you get your final x position. Okay, So we have run out of time, so I'm going to stop there. But if anybody has any questions, I'm happy to answer them. I'm going to stop the recording too.